Here we have a circle, and if we take a portion of its perimeter, blue part on the edge for example, then that's an arc on the circle. And an arc defines an angle at the center. So if we join up the ends of that arc with the center of the circle, then that defines an angle at the center there. And we can change the size of the arc and the size of the angle by dragging those endpoints. It also defines another angle at the perimeter of the circle. So if we place a point on the perimeter of the circle like that, and then we connect up the ends of the arc to it, then we have a second angle which is smaller than the one in the center, but they're both sort of connected to the same arc, or standing on the same arc is what we say there. And the interesting thing about this second one is it doesn't actually matter where that point is, it'll have the same size. So we can see that if we just drag this one round, it's 28 degrees all the way around there. If we change the size of the arc, it will change the size of the angle. So now it's 34.9 all the way around. Now what we're trying to do here is to prove that this smaller angle is always a half of the larger one, or that the larger one is always twice the smaller one. So that's what this proof's about. And a good way to try to do that is to split that shape, sort of that strange shape there in the middle, into two. And we can do that by dropping a line through the middle. And that's helpful because we've now got two triangles, which are probably easier to work with. We can just use the triangle properties to work this out. Because it's split these angles into two, then we might call this angle here the smaller angle, so we might call that S, and the bottom one we will call B. But before we do that, we actually might just sort of, to show the way it's been split, and then hide the S and the B. And the reason I'm doing this is, instead of calling them S and B for small and big, we might call them S1 and S2, because we've split S into two bits. So this side here we might call S1, and then the other side of that we'll call S2. So we're saying that S is equal to S1 plus S2. We've just split it into two. And the same with this angle B at the bottom. We'll sort of split that into B1 and B2. The reason why it's useful to split them into the triangles is we can use things like the triangle properties. So if we examine this triangle, those two lengths have marked are the same length because they're both the radius of the circle, from the center out to the edge, and from the center out to the edge there. So that's actually an isosceles triangle we've got here on the left, which means if these two sides are the same, then the two angles opposite those sides must be the same as well. We've already called this one up here S1, so it tells us this one here must also be S1. And then we've got another angle here which we don't really know anything about, so we might just call that, say, alpha. So based on that we can say, well, that we know all the angles in a triangle always add up to 180. So we can say S1 plus alpha, and we could say plus S1 again. Instead of doing that, we'll just write 2S1 is equal to 180. And then we also know that if we look around here, we can see that alpha plus B1 would also add up to 180 because it's the property of a straight line. So we can just say that alpha plus B1 must also sum to 180 because it's just a straight line around there. Now, if that's the case, then we've got two things that equal 180, so they must also be equal to each other. We can just say that 2S1 plus alpha must be equal to alpha plus B1. And if we look at that, we see we've got alpha on both sides, so we could subtract that alpha from both sides. We'll end up with 2S1 is equal to B1. Okay, so if we just put a bit of a box around all that. Now all of that has come from that triangle on the left. And we could go through exactly the same sort of argument on the right, because this side here is also a radius of the circle, so it's the same length as that one, which tells us that this must be the same angle as the one up the top. And we could label this one here, say beta. And we could go through exactly the same process there, and if we do that, we will find by exactly the same argument, we could say that 2s2 is equal to b2. You can do that if you like, it's just the same statement again. So if we know that, then we had originally said that we'd split this angle here, b, we'd split it into its two parts, b1 and b2. So if we say that b, which was the bottom angle, is equal to b1 plus b2, and we've just worked out that b1 up here is 2 times that portion of the smaller angle, and that b2 is 2s2. So we can say that b, let's just get rid of the b1 and b2, is 2 times s1 plus s2, just take out the 2 as a common factor there. And of course s1 plus s2 is the same thing as s. So we can say that b is equal to 2s. Now what we've just proved there is that the bottom angle is twice the top angle, and that's exactly what it set out to prove.